Hello everyone and welcome back to third law of motion states that when one object exerts a force on another object, the second object instantly exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects and never on the same object. The two opposing forces are also known as action and reaction forces. An alternate statement for the third law of motion is, for every action there is an equal and opposite reaction. Alright. So this is very logical, no? That for every action there is an equal and opposite reaction. It also happens in our daily life, right? So it is important to know that even though the action and reaction forces are always equal in magnitude, these forces may not produce acceleration of equal magnitudes. So the very important point here is that these forces act on different objects. So if they act on different objects, so it is a possibility that someone has greater mass and someone has a smaller mass. Suppose this is 5 kg and this is 8 kg, right? So they can have different accelerations, correct? Okay, so even when the force is equal in magnitude, they may not produce accelerations of equal magnitudes, right? So suppose, force is 40 newtons in both cases. Correct. So your acceleration in this case is force upon mass, that is your 8 meter per second square, and what is your acceleration in this case? 5 meter per second square. So you can see that even when the force is equal in magnitude, our accelerations are different. Why? Because our mass is different, right? So this is because each force acts on a different object. We need to take care of this. So we know that for every action there is an equal and opposite reaction. So force is same but our accelerations are different. Why? Because our force acts on different objects. Different objects, they can have different mass. So let's have some illustration of third law of motion. So let us consider two spring balances connected together. The fixed end of balance B is attached with a rigid support like a wall. When a force is applied through the free end of spring balance A, it is observed that both the spring balance shows the same readings of their scales. This means that the force exerted by spring balance A on balance B is equal but in opposite direction to the force exerted by the balance B on A. So they both are exerting force on each other, equal and opposite, right? So any of these two forces can be called as action and other as reaction. So we have equal and opposite forces. If you call this action, this is your opposite reaction, right? If you call this action, this is your opposite reaction. Simple thing is that if this applies force on this, this also applies force in the opposite direction. So for, and you see these both are two different bodies, right? A and B. Simply for every action, there is an equal and opposite reaction. So, illustration. When a gun is fired, it exerts a forward force on the bullet. The bullet exerts an equal and opposite force on the gun. This results in the recoil of the gun. You know this is recoiling. Since the gun has a much greater mass than the bullet, the acceleration of the gun is much less than the acceleration of the bullet. So the mass of gun is, if you have this gun and a little, that bullet which is put inside the gun, which has greater mass? Of course, mass of gun is greater, right? Mass of gun is greater than the mass of bullet, right? So and if they both have, from third law of motion, every action has equal and opposite reaction. So this means even if this, mass of gun into acceleration of gun should be equal to mass of bullet into acceleration of bullet. Why so? Because we know that for every action there is an equal and opposite reaction. So this must be equal. But we know that mass of gun is much greater than mass of bullet. Mass of bullet is very, less as compared to mass of gun, right? The gun has a greater mass. So this means that acceleration of gun has to be low and acceleration of bullet has to be very large, right? So that they both can be equal, because for every action there is an equal and opposite reaction. That's why that small bullet has such a great velocity, so that it has such a great acceleration, so that it applies great force. A bullet can kill someone. Why? How? Because it has, even when its mass is very small, its acceleration is too high, because this happens. One more illustration, because for every action there is an equal and opposite reaction. Just remember this thing. When a person jumps forward out of a rowing boat, the force on the boat moves it backward, right? So you can see, for every action there is an equal and opposite reaction, right? So one more illustration of the third law of motion. Request two children to stand on two separate carts. So due to COVID pandemic, we can't do the experiment together, right? So, but let's try and understand. So request two children to stand on two separate carts. Give them a bag full of sand or some other heavy object, okay? Ask them to play a game of catch with the bag. Does each of them experience an instantaneous force as a result of throwing the sand back? So there is a sudden force which they experience. Why? Because same thing, for every action there is an equal and opposite reaction. You can paint a white line on cart wheels to observe the motion of the two carts when the children throw the bag towards each other. So they both will be, exerting force on each other. So one more, this is the observation. The motion of two carts when the children throw the bag towards each other. When boy in purple throws the bag, he tends to move backwards. Right, he is trying to throw, he is tending to move backwards because of the reaction force. He is doing the action in the forward direction and the reaction is happening in the backward direction. Similarly, when the boy in red throws the bag, he also tends to move backwards. Why? He is trying to do action this side. Reaction will happen in the backward direction, right? Also, if the mass of the boy in red is less than the boy in purple, then the boy in red will move greater distance with greater acceleration in the same time interval when compared to the boy in purple, because we want equal action and reaction. Just like we saw in the case of bullet and the gun, right? So the velocity and the acceleration of bullet was too high to match the force of the gun. So let's consider the conservation of linear momentum. Let's know about this. So what was momentum? Your P. P was your mass into velocity, or m into v. Momentum was denoted by P and it was mv. So let's know about the conservation of linear momentum. Okay, so we will analyze it with the help of the collision of two balls. So suppose there are two balls. You have two balls and they have two different velocities. Suppose this is your ball A and this is your ball B. Okay. So your ball A has mass ma and your ball B has mass mb. Your ball A is moving with an initial velocity of ua and your ball B is moving with an initial velocity of ub. Okay. So they both are moving. Of course, your UA is greater than UB. If they have to collide, if they have to meet, then so this speed has to be greater than this speed. If UB is greater than UA, then what will happen? They will never meet, right? Because till the time it reaches here, the ball B will go further forward, right? So your UA, we are taking the condition that UA, your velocity of A is greater than velocity of B. So there will come a time when they will collide. And when they will collide, they will exert equal and opposite forces on each other. Right? There will be equal and opposite forces on each other. Okay, so for example, A and B collide. So there will be a force on B due to A and force on A due to B, right? So there will be force on A due to B and force on B due to A, right? And these both forces will be equal in magnitude. These are equal and opposite forces. Okay, so A exerts force FAB on ball B. FAB is force which A exerts on B. FB is force which B exerts on A. Okay. So conservation of momentum in collision of two balls. The momentum of ball A before and after the collision are, of course, first before collision. What was our momentum? Momentum is always our mass into velocity, right? So here for ball A, initial momentum is, P initial is MA into UA, because our initial velocity is UA, right? For ball B, your initial momentum is MA into UB, right? MA into MB, sorry, what am I saying? MB into VB, MB into UB. Initial MA into UA and MB into UB for ball B, right? This is your initial. And what after collision? Your final momentum is MB into VB for ball B, and for ball A it is MA into VA, right? So the rate of change of momentum. Let me take a slide and explain this to you in detail, so that it is very, very, very clear to you. 1 second. So I'll just take a blank sheet and now I'll explain you. Yeah. So there are your two balls, ball A and ball B. Okay. So both are moving balls. Okay. Both balls are moving. This has a initial velocity UA because it is for ball A, so we are calling it UA because both are initial velocity, so U and U, right? So for ball B we are giving initial velocity as UB. Okay. So now UA is greater than UB. Velocity of A is greater than velocity of B, so that they both can collide, right? So now your collision takes place between A and B, and then finally your A ball has some velocity VA and your B ball has some velocity VB, and they are moving. Okay. So now let's discuss three cases. So firstly we will be talking about initial momentum. So now what is your initial momentum? Initial momentum is a mass into velocity, right? So if our mass of ball A, let mass of ball A be MA, and mass of ball B be MB. So before collision, what will be your initial momentum? So initial momentum of your ball A, your momentum is mass into velocity, right? So MA into UA. And what is your initial momentum of ball B? Mass of ball B is MB into UB. This is your before collision, your initial momentum. And your after collision, what is your momentum, final momentum after collision? Mass of ball is again MA and your final velocity is VA, plus mass of ball B is MB and your final velocity is VB. Okay. So these are your initial and final total momentums. Okay. Now we will talk about change in momentum. Okay. If we are talking about change in momentum of A, of ball A. So for ball A, your initial momentum was MA into UA and your final momentum is ma into Va. What is your change in momentum? Ma into Va minus ma into ua. This is what you used to do, mv minus mu, right? So for ball A, it is ma into Va minus ma into ua. You take ma common, so it is a Va minus ua. And similarly for ball B, what is your change in momentum? It will be mb into Vb minus mb into ub. So we take mb common and Vb minus ub, right? So momentum of ball A before and after the collision are this. The rate of change of momentum is this, right? This and this, right? This is ma into Va minus ua. This is your force FAB, force by A, force due to A on B, right? And this is your FBA, force due to B on A. Okay. So now during collision what happens? For every action there is an equal and opposite reaction. During the collision, when both the balls meet, there is an action and reaction pair, right? So for every action there is equal and opposite reaction. So what will happen? FAB is equals to, during the collision, your FAB becomes equal to FBA. So we will simply equate ma into Va minus ua upon T is equals to mb into Vb minus ub upon T. Okay. So we get, what will we get? We will equate this, not written properly, but okay. So this is your ma into Va minus ua upon T. We will equate the momentum. We will conserve the momentum, right? This is your force, right? Is equals to mb into Vb minus ub upon T, right? So if they both are equal, what do we get? ma Va minus ma ua is equals to mb Vb minus mb ub. Then what do we get? That ma Va plus mb ub, ma Va plus mb Vb is equals to ma ua plus mb ub, right? So this is what we get from this. Okay. ma ua plus mb ub is equals to ma Va plus mb Vb, ma ua plus mb Vb, right? So we get that the total momentum of the two balls and the total momentum of the two balls before collision and after collision is conserved. That is that this is coming equal to this, right? You can just solve this, right? So since ma ua plus mb ub is total momentum of the two balls A and B before the collision, and ma Vb plus ma Va plus mb Vb is their total momentum after the collision, we observe that the total momentum of the two balls remains unchanged or conserved. This is your conservation of momentum, that your momentum doesn't alter. Momentum before the collision and momentum after the collision is same. Okay, so this is how we prove the conservation of momentum. This is very important. I hope you got this. So what does law of conservation of momentum states? It states that the total momentum can neither be destroyed nor be created. So it is unchanged or conserved by the collision. The sum of momenta of the two objects before collision and the sum of momenta after the collision is equal. Okay. So you can just analyze this before collision. Okay. Why? The same thing. If A and B are the balls, so MAUA and MBUB, and after collision some MAVA and MBVB, right? And during the collision and their change in momentum wise, the same thing, MV minus MU, right? MA, VA minus, these are the cases which we discussed in the previous case. So we can have three cases, right, for the collision. And what are the three cases we can have? First case is that when our one ball is at rest and one ball is moving some velocity, right, with some velocity. They collide, and what will happen after the collision? Then the ball which was at rest, it will start moving, and the other ball will be at rest. Why will this happen? Due to conservation of momentum. You know the formula which we derived in the previous slide, that ma ua plus mb ub is equals to ma va plus mb vb. You can actually put these conditions in this. So in this case, what is happening? Your velocity ub is 0 and it has some velocity u. You put it and you will finally find out that your va becomes 0 and your vb becomes equal to ua. Okay, in this case your velocity becomes equal to ua, initial velocity of the before like the previous ball, right, the other ball. So you can just check it by putting it in your formula. Okay, this formula, by conservation of momentum, you can just check this thing. What is your second case? Second case is when both the balls are moving towards each other with equal velocity. For example, this is u and this is minus u, like in the opposite direction but u, right? And the third case is which we discussed, right? u and some ua and ub, with ua greater than ub, right? So this is how you can derive all the things, right? So in this second case, what is happening? When they both will collide, they will change their direction, right? Okay, so this is what will happen, same magnitude but direction change. So this is one illustration of conservation of momentum. You can just perform this, right, to analyze the conservation of momentum. I hope this is clear. So these are the result. And what is the result of this experiment which you'll perform? When the tied knot of the balloon is released, air escapes from the balloon's mouth with greater speed. Thus, a reaction force acts on the opposite direction, that is from left to right, making the straw attached to the balloon on the thread move forward. Same thing, same phenomena. For every action, there is an equal and opposite reaction, and law of conservation of momentum takes place. Okay, another illustration for conservation of momentum. You can perform this also. So what happens? The test tube recoils in the direction opposite to the direction of the cork. So simply the cork is pushed in the forward direction by the hot steam. The test tube is pushed in the backward direction. Again, for every action there is an equal and opposite reaction, and momentum is conserved.